Hey guys, welcome back. We are looking at our next topic in this chapter, latent heat. So if you'll think back to chapter number 6, when we were studying the material there, we learned that during a phase change, so if a substance goes from a solid to a liquid state or from a liquid to a gas state, then during that phase change, the temperature doesn't change, right? And so we looked at some of the, if you'll look at page 402, you'll see the heating curve for water. And so we looked at some of those as we considered that chapter. And we see where the energy is still being applied during the melting and during the vaporizing. We've got a level spot on the curve. So the temperature is not increasing during that time, though energy is still being put into the system. And so we've got, whenever we're doing these energy analysis, we have to take that into account. Lost my marker. And so, what is that energy? There's obviously energy being applied on the graph there, but how do we calculate? How do we add that to our calculation and make sure that when we look at something that's going through all these phases here, that we have a true full energy analysis of what's happening? Well, we need to define something called latent heat. And so, latent heat is basically the amount of heat that is absorbed or released by a substance during a phase change. Okay, and so we represent, it's represented by capital L. All right. So make sure you know what that means. Make sure you know that that's what the capital L refers to. And we actually have two L's associated with a substance because there are two phase changes, right? You'll go from a solid, then it'll phase change into a liquid, and then it'll phase change into a gas. And so we have what we refer to as the latent heat of fusion, and that's represented by LF. And so that is basically the energy to go from solid to liquid. All right, and then the other one is LV, which is the latent heat of vaporization, and that's the energy required to go from a liquid to a gas. Okay? All right, so those are, make sure you recognize what LF and LV represent if you see those in a problem. And so here's the important thing before we can do this energy analysis. If you remember all of the equations that we had before, for heat, they all included change in temperature, right? So, since a phase change doesn't involve a change in temperature, we're obviously going to need a new equation if we're going to deal with the heat that is being absorbed or released during these phase changes. So, we've got a new formula that we need to make sure that we know, and that is Q equals mL, all right? And so the Q here, this represents the heat absorbed or released, right? Just like it did before in our other equations. M, just like in the other equations, M refers to mass. And then of course L is this new term, latent heat, which we just learned about. All right, now one other thing that I want you to know before we work some problems is that depending on what's happening, a substance, like I said, this latent heat, it will either be heat that is absorbed or it will be heat that is released. And so just to kind of make sure that you understand when each one happens. For example, for ice to melt, ice to melt, it should make sense to us that in order for the ice to melt, it's going to have to absorb heat, right? It's going to have to take heat in. So for ice to melt, it absorbs heat, right? So it takes this energy in, it takes this heat in, and it will absorb. But the opposite, if water freezes, the opposite is true here. If water freezes, then it's going to have to get rid of heat, right? So it releases heat. So I think just, common sense will sort of tell you, if you think about it properly, for ice to melt, it's going to have to absorb heat so that phase change will take place. In order for water to freeze and become ice, it's going to have to get rid of energy that it has so that it can actually, so that the molecules can slow down and it can go into the solid phase here. Okay, so with all of that in mind, let's look at example 13.4, which is on page 404. And this example is just a simple usage of this equation. Nothing very exciting, but let's at least go through that so that we'll know how to use this basic equation. And we'll write it down over here so that we don't lose track of it. So Q equals mass times L. All right, times latent heat. So this problem says water has a latent heat of fusion, which is LF, of 334 joules per gram. So LF equals 334 joules per gram, right? And then a latent heat of vaporization, which is LV, and that equals 2,260 joules per gram. So 2260 joules per gram, right? And if 150 grams of water freeze, what is that? That's our mass, 150 grams. If 150 grams of water freezes, how much energy is involved in the phase transition? And is the energy absorbed or is the energy released, right? So this is a very straightforward, simple problem. And it's just simply a matter of plugging in the appropriate numbers, right? So it's going from the liquid phase to the freezing phase, right? And so that's going to be this amount here. This is the energy that is taking place in that transition between liquid and solid, right? So that's the value for L that we need. And so our particular equation in this example is going to be M times LF, right? And so we just plug the numbers in, 150 grams times LF in this case is 334 joules per gram. And of course, grams are going to cancel out to give us a final unit of joules. And that amount is going to be 50,100. Right, so that's the energy that is required for the water to go from this liquid phase to this solid phase. And so the last part of the question is the energy absorbed or released? And so it should make sense to us that because it's cooling down, right, as it goes to this solid phase, the molecules which were more active in the liquid phase are now going to a phase where they're not moving around much at all. Then it must have to get rid of this energy, right, in order to slow down like that. So we have 50,100 joules of energy that is released during this process, all right? So now the cool thing is we've looked at all these different equations, right? We've looked at the, when we had our calorimeter experiments, we had the heat that was involved in the water and the heat in the calorimeter. And so we looked at both of those. We've got separate equations for each of those. And then now we've also learned about this concept of latent heat, and we have a formula for that. So we can actually do an energy analysis from beginning to end as a substance goes in between both of those phases as it transitions from solid to liquid and then liquid to gas. And that's exactly what we're going to do in this last example here. So let's look at example 13.5, which is on page 405. And the problem says this: a 125 gram ice cube is at a temperature of negative 8.7 degrees Celsius. At 1 atm, how much energy would it take to turn all the water in that ice cube to vapor? And then they give us the the specific heat capacity of ice, and they give us the latent heat of fusion and the latent heat of vaporization. All right. Now, why did they tell us that it was at 1 atm? The reason that they told us that is because we know then that the freezing point of water is going to be 0 degrees Celsius and the boiling point of water is going to be 100 degrees Celsius. Okay. So how much energy does it take it to go through both phases, to go from this state of being an ice cube all the way to becoming a gas, right? Becoming a vapor. So now we have all the tools that we need in order to figure this problem out. Just to write down quickly, it's 125 gram ice cube, and it starts at negative 8.7 degrees Celsius, right? And then they tell us that the C of ice equals 2.093 joules per grams degrees Celsius, and then LF equals 334 joules per gram, and LV equals 2260 joules per gram. All right, so there's the information that's given to us in the problem, right? So the first thing we've got to do is figure out the heat or the energy, however you want to use that, because heat is a form of energy. What's the heat that was required for it to go from this negative 8.7 degrees up to the 0 degrees Celsius? All right, so when we had our little curve, it went up, then it flattened out, then it went up again, it flattened out, then it went up, right? So we need to figure out what's the heat that's taking place during that little portion of the curve there. All right, so the change in T for the ice during that time is going to be whatever the final temperature was, which is 0 degrees Celsius, minus the starting temperature, which in our case was negative 8.7. So if we subtract negative 8.7 degrees Celsius, then that's going to give us a positive 8.7 degrees Celsius, okay? And then we can find out what the Q for the liquid was at that point. And so I keep dotting my I's twice. Always dot your I's twice. That way you'll be sure that your I's are always dotted. So our formula for that is M times the specific heat capacity times change in T, right? And so our mass is 125 grams. That's going to be times the value for the ice that we've got given to us here. So that's 2.093 joules over grams times degrees Celsius. And then we're going to multiply that times what the change in T was. So that is 8.7 degrees C. And so that's going to give us a grand total. The energy that was involved in this transition was 2,300 joules. Okay? All right. Now, of course, we're not done because we've got to figure out what happens energy-wise when we start at the bottom and go all the way to the top here. So let's keep track of that. So our first energy that we need to remember is the 2,300 joules. All right. That was the first part of our heating curve. What about the next part? The next part is we've got to calculate what was going on during this flat section of the curve right here, right? And so that's what we just learned about when we were discussing latent heat. So our new formula was the Q equals mL, right? And so again, our mass hasn't changed. Our mass is still 125 grams. But now we need the latent heat of fusion, right? And so we were given that, and that was given to us as 334. That's right here, 334 joules per gram. All right, so if we do the math on that, that turns out to be 41,800 joules. That was the heat for this portion of the graph right there, right? So let's make a note of that. 41,800 joules. All right. Keep going. All right, so that was that value during that portion of the curve. Now we've got to figure out this portion of the curve, right? From here to here. So what's that going to be? Now we're back to we're not using latent heat now. We're back to the the specific heat that we had learned earlier in the chapter. So this is going to be Q, again, Q is equal to M times C times the change in T. Well, nothing really changes from the first equation that we did. It's still going to be, well, I take that back. Actually, it does, right? So here the M is going to be 125. That doesn't change. Still 125 grams. But this time, our C is going to be, did they give us that? 4.184 joules per grams degree C. Oh, why don't we have that given to us? Because we had to memorize that. Remember that? When we were back on the only value that we said we need to make sure that we memorize is the value for the specific heat of water in its liquid phase. And that was 4.184. 4.184 joules per grams degree C, right? So that's why they didn't have to give us that, because we're supposed to memorize it. And then finally here, our temperature change is it went from the solid phase. This was the transition after the solid phase to the liquid phase, and then as it's heading towards the gas phase, we know that since the freezing point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius, that it went from 0 degrees to 100 degrees. So this is just going to be 100 degrees Celsius, right? That was the change in temperature during this portion of the curve. And so we punch all those numbers in our calculator and we get a value that is 5,200 and 5,200, oh, actually it's 52,300 joules, right? 52,300 joules of energy. So we're going to write that down. 52,300 joules, all right? And so now we've got our last little portion here, which is really just this, because we just need to know what happens right here. And at that point, it's going to be in our vapor phase, right? In the gas phase. So we're going to use the new equation that we learned for latent heat. But this time, because we're talking about the latent heat in this portion of the graph, we're interested in the latent heat of vaporization, right? So it's Q equals mass times LV. And so again, 125 grams, and LV is given to us as 2260 joules per gram. Grams will cancel out, and we get a final value of 283,000 joules. And that is our last piece of information that we need to be able to answer the question. The question was how much energy would it take to turn all the water in that ice cube into vapor, right? And so we've gone all along the curve. We've gone from here, where it was to start with, then from here, and then up to here, and then finally right here, right at the point that it becomes vapor, right? And we've got the energy for all of that. So the final answer to this problem, the Q total, is just going to be all of these energies added together, right? So 2,300 joules plus 41,800 joules plus 52,300 joules, and then plus 283,000 joules. All right, and so if we take precision into account, which we technically should, right, as we're adding all these up, we get a final value of 379,000 joules. That was how much energy was required for it to go to that frozen state at negative 8.7 degrees Celsius all the way to vaporization. Pretty cool, right? Who knew you could do that? All right, but wait, there's more. Another video coming soon.